The question is simple. Could we get energy from a black hole? The answer is yes. But the how is where things get strange. It's not about dropping a cable into one and pulling power out. The universe is weirder than that. To understand how we could power a civilization with a black hole, we first need to get a handle on what a black hole even is. Forget the sci-fi images of giant vacuum cleaners in space. The reality is both simpler and more profound. It all starts with gravity. We feel it every day. It's what keeps us on the ground. It's what keeps the Earth orbiting the sun. Isaac Newton described it as a force, a mysterious pull between objects with mass. Albert Einstein gave us a different picture. He said that massive objects don't just pull on things. They bend the very fabric of space and time around them. Imagine a flat rubber sheet. If you place a bowling ball in the middle, it creates a dip. If you then roll a marble nearby, it won't travel in a straight line. It will curve around the dip made by the bowling ball. That's gravity. It's not a pull. It's a curve. The more massive the object, the deeper the curve. Now, think about escape velocity. To leave Earth, a rocket has to travel about 7 miles per second. If it goes any slower, Earth's gravity will just pull it back down. That's Earth's escape velocity. A more massive planet like Jupiter has a much deeper gravity well and a higher escape velocity. You'd need a much more powerful rocket to escape from Jupiter. A black hole is what you get when you take this idea to its absolute extreme. It's what happens when you cram an enormous amount of mass into an incredibly tiny space. Imagine crushing the sun down to the size of a small city, or crushing the entire Earth down to the size of a sugar cube. The gravity of such an object would be immense. The curve in space-time would be less like a dip and more like an infinitely deep pit. At a certain point, the escape velocity becomes greater than the speed of light. Light travels at about 186,000 miles per second. It's the fastest thing in the universe. Nothing can go faster. So if the escape velocity from an object is higher than that, nothing can escape. Not even light itself. That's a black hole. The border where the escape velocity equals the speed of light is called the event horizon. It's not a physical surface you could touch. It's a point of no return. Anything that crosses the event horizon, a star, a planet, a beam of light, is trapped forever. From our perspective outside, it's just gone. This is why black holes are black. They don't reflect any light because any light that hits them gets pulled in. So the first most obvious idea for getting energy out is a non-starter. You can't just lower a bucket into a black hole on a rope, fill it with whatever's inside, and pull it back out. The rope would need to be infinitely strong, and pulling that bucket back across the event horizon would require more energy than you could ever hope to get from it. It would require an infinite amount of energy, in fact. The laws of physics say no. That door is closed. The energy isn't inside the black hole. The useful energy is in the region around it. The black hole itself is just the engine that makes it all possible. This brings us to the first real method. It's a mind-bending idea from a physicist named Roger Penrose, who worked with Stephen Hawking for many years. It's called the Penrose Process, and it only works with a specific kind of black hole, a spinning one. Most things in the universe spin. Stars spin, planets spin, galaxies spin. And when a massive star collapses to form a black hole, it doesn't just stop spinning. All of that rotational momentum gets conserved. The result is a spinning black hole. And a spinning black hole doesn't just curve space-time, it twists it. It drags the fabric of space and time around with it, like a spinning mixer blade dragging cake batter along for the ride. This region of swirling space-time outside the event horizon is called the ergosphere. It's a very strange place. Inside the ergosphere, space itself is moving faster than the speed of light relative to someone far away. This doesn't mean things inside are breaking the cosmic speed limit. It means that to stand still from an outsider's perspective, you would have to travel faster than light in the opposite direction, which is impossible. So once you enter the ergosphere, you are forced to move in the direction of the black hole's spin. You could still escape, as long as you don't cross the event horizon, but you can't stand still. Here's how the Penrose process works. Imagine you build a sophisticated probe or a capsule. You fly this capsule into the ergosphere. Once inside the swirling region, the capsule splits into two pieces. One piece is designed to be thrown into the black hole. The other piece is shot back out, away from the black hole to be collected. This is where the magic happens. Because of the weird physics inside the ergosphere, it's possible to jettison the first piece into the black hole in such a way that it has what physicists call negative energy. This is a tricky concept. It doesn't mean it has less than zero energy in some absolute sense. It means its energy is negative relative to an observer far away. Think of it like this. The black hole's rotation gives the capsule a massive energy boost. By throwing a piece away in just the right direction, you are essentially stealing some of that rotational energy. The piece that falls into the black hole pays the price. It reduces the black hole's spin just a tiny bit. Because energy has to be conserved, the piece that gets ejected back out must have more energy than the original capsule had when it first entered. It flies out with extra speed, extra momentum. That extra energy didn't come from a fuel tank. It came directly from the black hole's rotation. You have successfully harvested energy from the black hole. You could repeat this process over and over. Each time you send in a capsule, split it, and get a piece back with more energy. Each time, the black hole spin slows down a tiny fraction. Over billions of years, you could theoretically extract all of the black hole's rotational energy, which is a staggering amount. For a large spinning black hole, its rotational energy could be more than the energy the sun will put out over its entire 10 billion year lifespan. It's an almost limitless power source. Of course, the engineering challenges are beyond comprehension. We would need a civilization capable of building structures that can navigate the intense gravitational fields near a black hole. The materials would have to withstand being stretched and squeezed by tidal forces that would tear a planet apart. The timing of splitting the capsule would have to be perfect. It's a project for a civilization thousands or millions of years more advanced than our own. But the physics is sound. It is a valid way to get energy from a black hole. There's another way, and it's even stranger. It comes from the work of Stephen Hawking. It's called Hawking radiation, and unlike the Penrose process, it doesn't require a spinning black hole. No, it works for all of them. But it taps into something much deeper, the strange rules of quantum mechanics. One of the weirdest ideas in modern physics is that the vacuum of empty space is not actually empty. It's a boiling, bubbling sea of what are called virtual particles. These are pairs of particles, a particle and its antiparticle, that pop into existence from nothing, exist for a fraction of a second, and then collide and annihilate each other, disappearing back into nothing. This is happening everywhere, all the time. It's the background fuzz of reality. Normally, we never notice it because it happens so fast and cancels itself out. Hawking's great insight was to wonder what happens if a pair of these virtual particles pops into existence right on the edge of a black hole's event horizon. In this unique location, something new can happen. One of the particles might fall into the black hole, while the other one escapes out into space. Once the pair is separated like this, they can no longer annihilate each other. The particle that fell in is lost forever. The particle that escaped is now alone. It can't just be a virtual particle anymore. It becomes a real particle, it flies away from the black hole, carrying energy with it. To an observer far away, it looks like the black hole itself has just emitted a particle. It seems to be radiating heat, glowing ever so faintly. This is Hawking radiation. But where did the energy for this new real particle come from? It can't come from nothing. The law of conservation of energy still applies. The answer is just as strange as the Penrose process. The virtual particle that fell into the black hole is considered to have negative energy. When it falls in, it reduces the total mass and energy of the black hole by a tiny amount. So, the black hole pays the energy cost for the particle that escaped. This means that black holes are not truly black. They glow. And because they are constantly radiating away particles, they are also constantly losing mass. They are very slowly evaporating. This process is incredibly slow for the kinds of black holes we see in the universe, the ones formed from collapsed stars. A black hole with the mass of our sun would take more than the current age of the universe to evaporate even a tiny fraction of its mass. In fact, these large black holes absorb more energy from the faint background radiation of the universe than they emit through Hawking radiation. So, right now, they are actually growing, not shrinking. To get any meaningful energy from Hawking radiation, you would need a very small black hole. A black hole with the mass of a large mountain would be about the size of a proton. It would have a temperature of trillions of degrees and would radiate away energy with the power of millions of nuclear bombs. It would evaporate in a final, brilliant flash of gamma rays. Some physicists believe that such tiny, primordial black holes might have been created in the extreme conditions of the Big Bang. If we could find one and somehow contain it, it would be the ultimate power plant. But we've never found one. They remain purely theoretical. So while Hawking radiation is a real physical process, and it does mean black holes leak energy, it's not a practical way to power our world with the black holes we know exist. The energy output is just too small. This leads us to the third, and in some ways the most straightforward method of all. It doesn't involve stealing rotational energy or exploiting weird quantum effects at the event horizon. It involves something much more familiar: friction. Black holes are often surrounded by what's called an accretion disk. This is a massive spinning disk of gas, dust, and debris from stars and planets that have strayed too close. This material doesn't just fall straight in. Because of its own momentum, it gets caught in orbit and forms a flat, spinning disk like water spiraling down a drain. This accretion disk is one of the most violent and energetic places in the entire universe. As the material in the disk spirals closer to the black hole, it moves faster and faster, approaching the speed of light. But different parts of the disk are moving at different speeds. The inner edge is moving much faster than the outer edge. This causes an immense amount of friction. The gas and dust rub against each other, generating an incredible amount of heat. Think about rubbing your hands together to warm them up. Now imagine that on a cosmic scale, with entire stars worth of material moving at near light speed. The temperatures in an accretion disk can reach millions or even billions of degrees. It gets so hot that it glows with unbelievable brightness, blasting out radiation across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. In fact, the brightest objects in the known universe are not stars. They are quasars. And a quasar is simply the brilliant glare from the accretion disk of a supermassive black hole at the center of a young galaxy. The disk can shine hundreds of times brighter than the entire galaxy it lives in, a galaxy containing billions of stars. This process is incredibly efficient. While a nuclear fusion reaction like the one that powers our sun converts about 0.7% of matter into energy, the friction in an accretion disk can convert 10% or even up to 40% of the massive infalling material into pure energy. It is the most efficient energy generation process known to physics. So, how would we harvest this? In principle, it's the simplest method of the three. The energy is already being blasted out into space as light and heat. We just need to collect it. You would need to build a massive structure around the black hole's accretion disk, a kind of solar panel on an astronomical scale. Something like a Dyson sphere, a hypothetical megastructure that an advanced civilization might build to enclose a star. But this would be a Dyson sphere, built to capture the light from an environment far more hostile than any star. The structure would absorb the intense radiation from the disk, convert it into usable electricity, and then beam it wherever it was needed. The black hole itself isn't the direct source of the energy here. The infalling matter is. The black hole is just the gravitational engine driving the whole process. It's the catalyst that allows the gravitational potential energy of the matter to be converted into heat and light with unparalleled efficiency. Of the three methods, the Penrose process, Hawking radiation, and the accretion disk. And this last one is the most plausible for a future civilization. It doesn't rely on finding tiny hypothetical black holes or on technology that can manipulate negative energy states. It relies on a process we see happening across the universe. It's just a matter of cosmic engineering. But we have to be honest about what that means. The scale is almost impossible to imagine. The nearest known black hole to Earth is still over 1,000 light years away. We currently have no way to travel even a single light year in a human lifetime. Getting there is the first impossible hurdle. Then there's the environment. An accretion disk is not a friendly place. It's a maelstrom of high-energy radiation and extreme gravity. Any structure we build would need to withstand a constant bombardment of X-rays and gamma rays that would sterilize any known form of life and degrade any material we know how to make. It would also need to maintain a stable orbit in a complex gravitational field, avoiding being torn apart by tidal forces, or simply falling into the disk itself. So, could we harvest energy from a black hole? The laws of physics say yes. There are at least three distinct ways it could be done. We could steal a black hole's spin, we could collect the slow trickle of its quantum evaporation, or we could harness the brilliant violent light of the material it's eating. But could we, humanity, do it? No, not anytime soon. This is not a technology that will solve our energy problems in the next century, or even the next millennium. This is the kind of project reserved for what scientists call a Type the Second or Type the Third civilization. On the Kardashev scale, a civilization that can harness the full energy of its parent star or its entire galaxy. We are still a Type 0 civilization, struggling to even manage the energy resources of our own planet. Thinking about harvesting energy from a black hole is not a practical engineering exercise for today. It's an exercise in imagination. It's about pushing the known laws of physics to their absolute limits to see what is possible. It tells us that the universe contains energy sources so vast that they make our own sun look like a tiny candle. It reminds us how much we still have to learn. The theories tell us the energy is there. The black holes are out there. The gap between what is possible in theory and what is possible in practice is, for now, as wide as the distance to the nearest star. But knowing that it's possible at all is a profound thing. It changes how we see these dark, mysterious objects. They aren't just cosmic dead ends, they are potentially the ultimate power source in the universe.